Christmas, everybody. Ho, ho, ho. Today is Monday, December 25th, 2017, and this is Before the First Cup of Jules here at UCY.TV. Happy Monday, everyone. Merry Christmas. It is a 26 degrees with 50-mile-an-hour gusts with lots of snow and Christmassy here in upstate New York. So where do we leave off on Friday? We titled the show Self-Assembling Programmable Matter, DARPA, MIT, Drexler, and Grey Goo. We took a lot at nanotechnology and some of the things that are happening with this programmable matter to make a chair turn into a table, to turn into any of a myriad of Internet of Things, embedded sensors in everything that'll be able to feed data back to Central Command. So today, I thought we would have a little treat. Since I mentioned Eric Drexler, we are going to listen to a lecture from Oxford University by Eric Drexler titled Remaking the 21st Century. He talks about a lot of interesting applications and different ways that they can utilize these new methods of manufacturing with all the physical laws of physics to be able to recreate our reality. So I hope you enjoy it, and hopefully tomorrow I will be back live. Hope everyone has a wonderful holiday, and I will catch up with you tomorrow. Take care.
I'm Eric Drexler, and I was drawn into the field of what's now called nanotechnology when I was a student at MIT back in the 1970s. And the center of my work has been understanding what physics tells us about technologies that don't exist today, but that could be developed in the future.
So the title that I thought might be a good title for this talk is Remaking the 21st Century. And what I mean by that is the prospect of having the coming decades be very different from what people expect, because of a fundamental change in the physical technology base that we operate our civilization on. You mentioned nanotechnology and what its effects are. The main effect are the effects of the $100 billion nanotechnology manufacturing industry in the world today and its products. We call them cell phones, computers, in general, integrated circuit chips today. They entered the world of nanoscale features over a decade ago. They're now deep into the nanoscale range. They're intricate systems with billions of nanoscale components working together at high frequencies, doing complex operations. And it's very odd that this nanoelectronics is not called nanotechnology, while work in materials science is. And as we'll see, another oddity is that the main area of advance in the kind of nanotechnology that in the long term I think will be of overwhelming importance, which is the molecular nanotechnology. The advances there in atomically precise fabrication have been primarily in the molecular sciences, and again, aren't called nanotechnology. So one of the reasons I say blamed for the term nanotechnology is that it has become very confusing. And I'm more inclined currently to speak in terms of atomically precise fabrication and atomically precise manufacturing. So if you think about the difference between the old Stone Age and the new Stone Age and the Industrial Revolution and today, it becomes rather obvious that what we can do in the world depends overwhelmingly on what we can make. If you can build spacecraft, you can go into space, and if you can't, you don't. If you can build nanoelectronics, you can have an information technology revolution. And if you can't build those kinds of systems, you don't get those results. So the prospect of a fundamental transformation in the way that we make things opens the prospect of a fundamental transformation in the range of capabilities that the human race has, the problems that we face, the problems that we no longer face, and the sorts of considerations that are shaping expectations of the 21st century and strategic moves by nations like China and the United States. Many dangerous developments and that are based on expectations that may prove to be wrong. And I think it's important to get our expectations in line with reality if we can get a better picture of what that reality might be. So like to say sometimes, there's nothing small about nanotechnology. It's really about fundamental structures in the world and scalable technologies that can have a very large impact. And just to anchor the idea of very large impact, we have a trillion-ton atmospheric carbon problem these days, which is looking rather intractable with present industrial technologies. But there is a sense in which this can be viewed as a manufacturing problem. I think it's useful to take a stance which says that if a problem can be addressed by, substantially solved by proper applications of a new manufacturing technology, then one can consider the problem to be a manufacturing technology problem. An example, if we were able to make today low-cost, lightweight, easily deployable, efficient photovoltaic arrays, and also inexpensive, effective means of interconverting electrical and chemical energy, making carbon-neutral liquid fuels, a few other operations like that, we would be able to rapidly deploy an infrastructure that would make coal-fired power plants, gas-fired power plants uneconomical. They would no longer be built. And if this infrastructure were sufficiently inexpensive, no one could afford to burn coal anymore. It would simply be not economical. The reason we can't do that is a manufacturing problem. We cannot make the requisite physical systems at low enough cost and large enough quantities. And I will return to issues of energy and climate change, climate disruption a little bit later, and talk about prospects for actually reversing the accumulation of greenhouse gases rather than slowing emissions and then waiting for geophysical processes to draw atmospheric levels down over a period of decades and with a tail extending to centuries, as natural processes would do. So this is a talk that's in some sense about the future, but in some sense it isn't. And to understand that there is knowledge to be had here, not just, speculation and projection and, gee, maybe this will happen and maybe that will happen. To understand that there's actual testable, reliable knowledge to be had, it's important to understand what the question is. So what I've asked is a different question. The standard questions, people maybe try to predict scientific discoveries. Well, that's absurd. If you knew what the discovery would be, you'd already know it, and so it's a logical contradiction. Predicting specific technological developments. Well, future inventions have again and again and again been surprising. It's very hard to predict what will be invented by ingenious people in the future, and therefore this kind of prediction is also not very practical. Winning technologies. 10 years from now, what will be the dominant technology in this area or that area? Often unknown, because it depends on a balance of competitive technologies, it depends on the development of standards, range of market forces. What one can do is ask questions about the timeless potential of technology. Because the potential of technology is something that is dependent on physical law and not dependent on anything else. And by potential, I mean what kinds of physical artifacts can exist and what kinds of behaviors can they exhibit. If you look at the structure of mathematical proof, this whole world that people are still exploring of mathematics is in some sense implicit in a set of axioms. The whole world of potential technologies is in some sense implicit in the laws of physics. And just as we can analyze and model systems that can't be built, one can understand a lot about planets without being able to build a planet, just as we can plan trajectories for spacecraft through the outer solar system before actually flying a spacecraft on that trajectory, one can use physical law to understand something about the potential of technology if you ask the right questions. And the trick is to ask questions that can be answered, to very deliberately reason from a base of well understood textbook quality physics and engineering, not guessing about what might be discovered, not speculating on what inventions might occur in the future, but instead describing systems that can be analyzed in a straightforward way, in a way that looks like a set of problems that you might find at the end of chapters in a physics textbook. Okay, that level of analysis. And it turns out you can go quite a long way by doing that. It's not science because it's not studying nature. It's not conventional engineering because one isn't designing something to be built in the near term so that the company will pay you to do the work. Instead, it's applying this methodology is one of applying engineering principles to understanding potential technologies that are designed to be analyzable and not designed for high performance per se. So the questions that arise in looking toward the potential of technology in a pathway sense, there are really two. One is what can be made with present tools. That's the standard engineering question. What can we design and make with existing capacities in the laboratory and factories? The other question is, what will further progress enable? How far can one go? Where does it lead as you use tools to build better tools? You know, if you look at the things around us, aside from the people, pretty much everything here was made by machines. Sometimes with varying amounts of help from human hands, and increasingly by thoroughly automated systems. Where did those machines come from? Well, by and large, they were made by other machines. And where did those machines come from? Well, if you trace it back from the sort of the leaves of the technology tree, which are around us, through the branches of machines building the machines that build these consumer products, you trace it back, you find what can be thought of as the trunk of the tree. The machines that build the machines that build the machines, the core of the industrial capital structure, which tends to center on machines that cut steel and make precision shapes that can be used to implement machines that cut steel and do other things. And then if you ask where those came from, well, they were made by machines with increasingly the aid of human hands, but less precise machines with materials that weren't as sophisticated. And if you trace it back and back, you find a blacksmith hammering away on iron, and sometimes a blacksmith making new tools, better tools, and passing them on to the next generation in a line of progress that led to the Industrial Revolution and to where we are today in macroscopic technologies. And I'll say a little bit more shortly about a path forward from the present-day capabilities in the molecular world that is broadly parallel to that pattern of historical technology development. This is a picture of one representation of a protein molecule. This shows what the pattern of the backbone is. It's actually two superimposed structures. One was the result of computational design. The other structure is the result of X-ray crystallographic mapping of an actual physical protein that was made according to that design. This particular design, top 7, marks a particular landmark or milestone in the development of a field called protein engineering. It was the first one that had a completely novel fold. And the reason I mention that is that in the molecular world, the path forward, the most attractive path forward, leads from our current abilities to do atomically precise fabrication, and that's an atomically precise structure. Here's one representation of the atomic structure, and here's another with the space-filling pattern. It's a piece of plastic. It's a polymer with mechanical properties that are comparable to epoxy or lucite, components that can be used to build a certain quality of machines in the macroscopic world. These materials, some of them are comparable in stiffness to wood, which is also something one can build machines from. So today we have not, blacksmithing. Instead, we have the ability to design and fabricate macromolecules with distinct shapes and functions. Looking in biology, we find a very wide range of functions. Motors and sensors and actuators and chemical processing systems and machinery like the ribosome, which takes in digital information and uses that to guide the fabrication of protein molecules, which then are components of machines, including the ribosomes. Now, back in 1981, I published a paper in the U.S. National Academy of Sciences proceedings, which argued that protein engineering was possible. At the time, it was thought to be impossible because people thought that you had to understand how natural proteins would fold before you could design proteins that would fold. And I pointed out that the scientific problem of figuring out how a natural protein would fold is fundamentally different from the engineering problem of designing something that will behave as you want, that will fold according to plan. And people said, that's interesting. Dubbed that the inverse folding problem. And the citation tree grew out of that, which led to the field of, now burgeoning field, quite large field, of protein engineering and this particular milestone. So that is a line of development in atomically precise fabrication of components that can be used to build machine systems, and it's not called nanotechnology. I pulled strings and got one of the people behind this work to be awarded a Feynman Prize in nanotechnology. And a colleague later told me that, yeah, he was around when this guy, David Baker, University of Washington, heard that he was going to be awarded the Feynman Prize in nanotechnology, and he asked, why? What have I done in nanotechnology? Atomically precise devices that can be used for building machines. And by the way, when you think of proteins, don't think of meat, think of the horn of a bull. Alpha keratin is an example of a protein. It's a respectable engineering material. Young's modulus of elasticity of about 1 gigapascal. So, looking at the progress to date in atomically precise fabrication, the long sweep goes from Wohler's synthesis of urea in 1828, 8 atoms, up through modern work in the structural DNA, where people are routinely designing structures with 1 million atoms, scale of 100 nanometers, with a degree of reliability that resembles carpentry. You use the double helix as a rod, as a structural member. You use the pairing interactions to direct assembly in a specific way. You bundle the rods together by having the helices exchange strands so that they're held together by this crossover. And that has proved to be a way of making a very wide range of structures that can now be integrated with proteins to build systems that seem to open some doors to developments that are far along the path of what I will be outlining in a moment. So, in human history, we've seen tools used to build better tools. I mentioned blacksmithing, on to the Industrial Revolution, and on to today's dominant nanotechnology, which again, confusingly, is not called nanotechnology, which is the integrated circuit technology. If you ask, where can atomically precise fabrication go with machines being used to build better machines? The answer seems to be remarkably close to an ability to build sort of more or less any stable inorganic structure in atomically precise configurations that can be functional in various ways. Semiconductor structures that are smaller than we can do with today's top-down fabrication, with precision. Some of the advantages of atomically precise surfaces like specular electron reflection, so you actually have less resistance in a thin wire. Non-semiconductor computational devices. High-quality machines. Materials of extraordinarily high strength-to-weight ratio, very wide range of products if you could do that. And to understand that area, again, is a matter of looking at this timeless landscape of technology that is implicit in physical law. So this is a two-dimensional diagram of a high-dimensional space of performance metrics. So one dimension in the space might be the speed of transmission of a signal. Another dimension might be speed of flight of a spacecraft. Another might be the density of computation, how much computation per unit time in a volume of 1 cubic centimeter with a power of 1 watt. Okay, so that would be a dimension. How good the refrigerator is in your kitchen. Now, the performance metrics for that, another dimension. In any dimension, you find ultimately there's some physical limit. In some cases, it's simple. Speed of transmission of information, we've reached that limit. It's the speed of light. Send photons, there you are. The speed of motion of massive artifacts is a tiny, tiny fraction of the speed of light is all that's been accomplished. We're very far from that limit. In computation, we don't really know where the limits are. The upper bounds that come from physics are absurdly high. They're upper bounds, but it's clear there must be some tighter bound because you just can't do what the very fundamental limits suggest you might if you drop the reality of matter and just keep quantum mechanics in a more abstract sense. So there's a domain between what's been demonstrated, what exists by engineering, what's clearly forbidden by physics, and in between there are physical systems that can exist and function, and some of them can be designed and analyzed. So that domain for exploration is what I term here exploratory engineering. And I said a little bit before about how that relates to science and engineering. It sort of falls into the cracks between them. And the characteristic activity is to define designs out in this space that is of possibilities, that is beyond current engineering practice, and analyze them, and set a lower bound on what can be accomplished in the real world, given a fabrication capability. Someone undertook this exercise in understanding spaceflight some time ago. Is widely known as the father of astronautics. After the Soviets threw him in prison for a while, they then let him out and called him a hero and gave him a pension. And he worked out the basics of astronautics, chemical-fueled rockets, what was required for life in space, trajectories, velocities, a lot of quantitative analysis, what would be the best fuels. And he worked that out in by lamplight in a log building. He worked by day as a school teacher, invented astronautics in the evening, and his name was Konstantin Tsiolkovsky, and he did his key work in the late 1800s. How could he do that? Well, physics doesn't change, and he was able to explore some of the implications of physics and strength of materials and the energy of combustion of hydrogen, liquid oxygen, to understand some of the potential performance of space vehicles. So he identified, some points out in this space that have since been reached by technology. And in a broadly similar way, we can look at points that can be reached by atomically precise fabrication technologies. And ongoing exploration can describe an envelope of possibilities where you can be confident that technology can go at least this far, and to be really confident means you have a rather high confidence that it will in fact be able to go further. So that is the nature of the game, and some of the most interesting possibilities come from some particular materials and some particular kinds of devices. The materials are strong covalent solids, materials like diamond, silicon carbide, graphene, aluminum oxide, a whole family of materials that have a strong covalent character in their bonding. They are light elements high in the periodic table, high and to the right. They're common elements, and they form strong, low-density materials that, it turns out, can be very well modeled by existing computational chemistry software. The computational models that can describe flexible molecules and how they behave in solution are more than accurate enough to describe the same kinds of bonds in rigid configurations where you don't have water molecules around. So the tools that have been developed for practical problems today are actually better than what is necessary to analyze this kind of structure, and machinery that can be made from these structures when one is able to fabricate them. And regarding fabrication, this kind of computational analysis can be used to guide the design and validation of fabrication processes that work by guiding reactive molecules on specific trajectories, keeping them from from encountering targets that they should not encounter, avoiding reactions that should not happen, which turns out to be the primary problem in controlled chemical synthesis, not to make reactions happen, but to make all the rest of the reactions not happen. By guiding the motion, one can prevent the wrong reactions from happening, make the right reactions happen. In this case, it just shows the simplest case of depositing a hydrogen atom someplace and removing one. The ability to shuffle hydrogen atoms around on a surface is important. So, if one has atomically precise mechanisms that can guide the motion of reactive molecules, then one would be able to build atomically precise rigid structures of the sort that are necessary to build atomically precise machines that can guide the motion of molecules. So just as today we have an industrial infrastructure based on steel tools where collectively the machinery in the factories in the world can make all of the kinds of devices that you find in factories and more, which is why we have products other than factories just producing factories, and also why we see better technologies over time. So in the world today, we have a capital infrastructure where machines make machines in a comprehensive, coherent way. We now can understand how a similar comprehensive set of fabrication processes making the kinds of machines necessary to perform the fabrication processes, how that can function in the nanoscale world. So the key is rigid, atomically precise machines. And in my book, which I meant to mention, the first slide had the title of my book, and in the lower left it said Oxford Martin School. And I would like to thank the Oxford Martin School for inviting me here from the United States to finish work on that book, which was published not terribly many months ago, and also for inviting me to stay long term. I now have no plans to be anywhere other than Oxford for the foreseeable future, because I like it here a lot. So that's something I intended to say with the first slide. Missed entirely. Okay, so diving back into the midst of rigid, atomically precise machines. What do we mean by machines? Well, things like gears and bearings and shafts and motors and sliding things and 4-bar linkages and toggles and detents and all the little things that mechanical engineers use to make articulated machines that solve motion problems, move things and put things in place and so on in a factory. And some samples of the kinds of things used in these machines are found in, all of these gears might be found in places like an automobile power transmission chain and many other places. So these are some relatively complicated cases of gears. And as test cases, they're kind of interesting. One can design functional equivalents of each of these at a scale where the diameters of these objects are that are shown here. The first two characteristic dimensions are maybe 3 nanometers in diameter. The spheres all represent atoms. The atoms are carbon, silicon, hydrogen, nitrogen, oxygen, and sulfur. One of them also has some phosphorus. All common materials in the, again, upper right-hand corner of the periodic table. And the configurations can be modeled by doing energy minimization in a computational model of these molecular systems. And one can also do molecular dynamics and examine their motion, power density, energy dissipation, and so on. It turns out that physics likes these. These things work remarkably well. Friction can be remarkably low. Static friction can be remarkably close to zero, at least for bearings, and pretty good for rolling gears. I could go on. There are many characteristics that make problems that are prominent in mechanical engineering go away in this domain. Excuse me. Yes.
These things exist, or are they like?
These are computational models.
Yeah, but are they models of something that was created?
No, these are models of. If we're doing blacksmithing today, these are models of. Okay, the gears to the left are to blacksmithing, more or less as the gears to the right are to present-day macromolecular synthetic methods. They're out of reach. We can understand what kinds of tools could build them. We can model them with great confidence and more than adequate accuracy for engineering purposes with present tools. But these were made by at a computer screen, saying where the atoms are and where the bonds are, and then turning on simulated physics to see how they behave. So there are some characteristics of this class of technologies. I say physics, quote unquote, likes them. Physics is telling us that this is a great way to do manufacturing, and for two reasons. One is matter is made of atoms and molecules, and if you work with the fundamental building blocks, you can do things that you can't if you're just pushing matter around in a sloppy, messy way, cutting and molding and doing etching and so on. The other one has to do with speed. For machines, generally speaking, the characteristic speeds in meters per second are independent of size. That's just, if you do that, you find that the accelerations are the same, the stresses in the materials are the same, the ratio of vibrational frequencies to mechanical motion frequencies are identical, the shapes traced in space-time, you scale space and you scale time equally, You're keeping velocities constant, you end up with the same shapes and patterns of stress. So that's natural scaling. And it follows from that the time for a motion, one rotation of a bearing, one reciprocating motion of some other mechanical element, is proportional to scale. Twice the distance, twice the time to cover the distance. By the same token, operating frequencies are inverse to scale, and if you scale your machines down by a factor of 1,000,000, from say 1 cycle per second, you get frequencies that are a megahertz. And in the world of microscale machines, this is commonplace. You see megahertz frequencies quite, in vibrating devices in micro machines quite routinely. And again, same materials, same stress, etc. Purely a matter of scaling and mechanical scaling laws. So looking at these gears and so on, the actual scale factor for roughly equivalent systems is about a factor of 10 to the 7. And if you consider that in the context of manufacturing, a system that's moving parts and putting them together, if you scale the parts proportionally to the machine, then the throughput percentage of the machine's mass processed per cycle is scale independent. The throughput in terms of kilograms per second per kilogram of machine mass depends on the frequency of machine operation. And therefore the scaling provides a factor of 10 million in throughput per unit mass, which is comparable to the difference between chemical explosives and thermonuclear explosives, sailing a ship around the world and sending a vehicle out of the solar system, or working with an abacus and having a silicon computer at gigahertz. It's that kind of ratio. Actually, that one's a larger ratio. But there are very few ratios that large in engineering, and this is one that physics is promising us, given that we build machines of this class. So, devices, you make machines, build factories, mechanical engineers know about this kind of thing, provide the right palette of components, you can build a certain range of machines. Axioms give you a superstructure of theorems, components give you a superstructure of feasible systems. And that knowledge transfers. You can make analogous components, you can build analogous systems, and do a wholesale importation of knowledge from mechanical engineering to this domain. The bearings work differently, but they're bearings. The gears interact differently when they mesh, but they're gears. And it's not much more different than the difference between building out of metal or plastic in many respects. I guess that's true more of the fabrication processes, which have great diversity. There are a couple of conceptual tools. One is, looking at the current leading nanotechnology, digital electronic systems, and then comparing those to prospective, not here yet, prospective nanomechanical systems for guiding the motion of molecules and doing fabrication. In digital electronics, you have arrays of nanoscale devices, gigahertz frequencies. They make patterns of bits and bytes and do general purpose information processing. Not specialized machines. Here's a telephone. There's a television. Over here is a camera. Over here is a dark room. Instead, you have digital devices that do all of these things, which would have greatly surprised engineers. The underlying principle is working with very small, discrete parts at high frequencies using a general purpose mechanism. Very analogous in atomically precise manufacturing. Arrays of devices, here mechanical. Nanoscale size giving higher frequencies, only megahertz rather than gigahertz, because electronics is faster. Patterns of bits and bytes on one side correspond, abstractly at least, to patterns of atoms and molecules. Discrete components, the smallest components in their domain. It turns out that the operations can be discrete and made insensitive to thermal noise, to thermal fluctuations, using physical principles that are essentially the same as what you find in electronics in terms of having a distinct energy gap, a distinct energy barrier between the right state and the wrong state, and always having a discretization of results. And the final parallel is that the result is general purpose physical production. Rather than having a host of specialized kinds of manufacturing. This is a kind of manufacturing technology base that would be more like 3D printing in having its breadth of potential products. Let's see, precision follows rather directly. You can see how a process like this might be clean because you're not, diluting toxic materials in water and then dumping it into a river. Instead, you're controlling the flow of materials with precision. Fast. It turns out that efficiency follows low resource consumption. Better materials, you need less of them. Common materials, don't go to war in Africa to fight for tungsten and molybdenum. Opens new realms of technology, obviously. And again, I would emphasize that this class of technologies that I'm describing here, not yet physically accessible, is very accessible to design analysis exercises. Textbook physics and chemistry, if there's anything new, it's a mistake. And the great power of it, some of the surprising consequences coming from elementary mechanical scaling laws. So again, parallel, 3D printing. Imagine that you had something like a 3D printer. Simple raw materials in, digital information in, energy in, things happen inside, parts move around, small bits of matter are arranged in a way controlled by your digital inputs, and out comes sort of any shape of object within certain tolerances in these additive manufacturing systems. Well, imagine that you have boxes, again, simple materials in, energy, digital information, arrays of very small high-frequency devices giving much higher throughput. Digital printer, 3D printers often take hours to produce a product. Here, the times are for something more massive and more intricate would be typically measured in minutes. A wider range of materials than can be made by industry and laboratories today, rather than a narrower range, and with the precision being atomic precision rather than a relatively coarse-grained. So, analogous to 3D printing, analogous to digital electronics, notable differences from both, but a lot can be understood by thinking in terms of those analogies. So I'd just like to quickly walk through some known possibilities, which largely follow from being able to make small things and to make strong materials and products at low cost. Set of comparisons. Supercomputers, more or less present generation. This is a little while ago. Megawatts, tons, hundreds of millions of dollars is the sort of scale. A device with a similar computational throughput, but made with atomically precise manufacturing, could have 1,000 times the information throughput, be an air-cooled device, and you can see lots and lots of zeros in the ratios for power, weight, and cost. Aerospace, aluminum structures have been costly to make. It's hard to make them with low enough defect rates to be reliable. The materials are stressed toward their limits, and they end up being rather heavy. Most of the mass that a space shuttle put up into space was the vehicle, and not the payload. Better materials, lower cost, defects that are scarce and nanoscale points to the ability to make vehicles that have a small fraction of the mass, makes it much easier to access space. Much, much lower cost, order of $1 per kilogram instead of $100,000 per kilogram, and greatly much more reliability. So one unexpected aspect of the 21st century, given that one crosses some key technology thresholds here, is that the world becomes larger than the Earth. All these science fiction dreams of the human race and Konstantin Tsiolkovsky's dream of the human race expanding beyond the Earth. The problem there has been a manufacturing problem. We can't make spacecraft with high performance and low cost. With superior manufacturing, a lot of science fiction all of a sudden moves from the, well, that was a nice dream category to, oh, we can do it. Speaking of aerospace systems and lower cost and higher performance, the ability to expand for a given investment, expand the size of arsenals by a factor of 1,000 is enough to suggest why there might be a temptation for an arms race in this technology. There are many, many other potential applications in the military area. And one of the main reasons that I have been attempting to articulate a picture of the prospects here, and a fairly comprehensive picture, in turn, not a narrow slice, but a broad picture of consequences, is because there are some very important decisions to be made at the level of national policy that make a difference between a cooperative path and a path to an unstable and dangerous arms race. And I'll point to a reference that goes into that further at the end. So, more benign applications. Today we have limits on food production. Arable land is getting scarce. A substantial fraction of the Earth's net primary photosynthetic production is now channeled into agriculture. The most productive and attractive for living things ecosystems in the world are precisely the places where agriculture works well, and therefore many of the more vibrant parts of the biosphere have been paved over with soybeans. If you could increase the productivity of agriculture by a factor of 10 and make it less dependent on weather and climate, you could decrease the footprint of agriculture, increase total food production, decrease pollution of water, move agriculture to areas that are not biologically productive spontaneously. And the key is solving a manufacturing problem, which is being able to make at low cost and large quantity the physical capital infrastructure necessary to do enclosed greenhouse agriculture. Increases in productivity are known. It's just too expensive today. Why? The cost of making the necessary physical artifacts. So one more area is energy. As I mentioned earlier, if we could make superior photovoltaics at low cost, the energy situation and greenhouse gas emission situation would very rapidly look different. Today, photovoltaics are relatively expensive, fragile. Mounting them is a large part of the cost. It will be a larger fraction of the cost as the cost of the cells declines. But if you're able to make photovoltaic devices that are small and made of robust materials and can be embedded in a matrix that is strong and flexible and can be made to adhere to surfaces and be tough and abrasion resistant, and produce rolls, kind of like rolls of black plastic of this stuff at low cost per kilogram, then one can look at a future in which we take roads and they become darker roads, and basically you resurface them with a tough, abrasion-resistant photovoltaic material. And simply resurfacing roads and rooftops is enough to produce on the order of the amount of energy that civilization consumes today, the rough order. And there are also prospects for decreasing the amount of energy needed, and of course there's a lot of land in the world that does not consist of roads and roofs. This is a sort of an example of how much one could reduce the footprint of an industrial civilization by solving certain manufacturing problems. And I would like to return to the most famous global problem of the day, which is greenhouse gas accumulation and climate disruption. What has been observed to date is a very steady and actually accelerating rise in CO2. And this Mauna Loa Observatory has this data series going way back to the late 1950s. And the world being what it is and the U.S. being what it is, they're being defunded, apparently. They're looking for they should run a Kickstarter, I suppose, to maintain this data series. But expectations are, given that people are working their way out of poverty by using today's industrial technology, and it's a little bit hard to say that's a bad thing, is that CO2 emissions are going to continue. And if they continue at their present rate, the levels will continue to climb at roughly the present rate. And it's more likely that emissions will increase rather than decrease, and that the rate of increase in CO2 will increase as well. So that is the pattern of expectation, and increasingly that seems to be a very bad thing. I'd like to have a future that looks something more like this, where the levels don't just level off, but are brought down to the pre-industrial level, preferably rather rapidly. Oh, why can't we do that? Well, again, it's a manufacturing problem. It requires a lot of energy. The thermodynamic work of compression of this dilute CO2 gas, the excess above industrial levels that's expected in this time frame, it's about 10 to the 21st joules of free energy required. You need devices that capture CO2 molecules, transfer them to a high density of CO2 to liquid density, if that's done thermodynamically efficiently, it's about that much energy, and there are ways of doing it with that kind of efficiency. For scale, that's 30 terawatt years of electric power if you use electric power, which is appropriate for running compressors. Current global electric power production time average is about 3 terawatts. So this is one civilization decade worth of electric power. Well, which has to, of course, be from non-carbon consuming sources to make this be of any use. Well, that turns out to be a manufacturing problem. If we could build photovoltaic arrays with the area of that little green square, which I've put here in the empty quarter of Saudi Arabia, which seemed like a good place, empty quarter, the equivalent of that area in the course of 10 years would provide enough energy to accomplish this task of CO2 removal. I very much suggest that no one count on being able to do this. If people start saying, "Oh, don't worry, because we'll be able to do that," we'll join with people in green politics to say, "Don't assume this." But it is a real prospect. Again, a manufacturing technology problem. So here to there, pathway. A lot more can be said about pathways than could be said a couple of years ago, but abstractly and generally speaking, one needs to develop manufacturing capabilities that are beyond what we have today. Therefore, they can be regarded as places in this possibility space that I outlined earlier. And some of these potential developments are stepping stones, tools that can be used to build better tools, leading to a threshold of scalable, atomically precise fabrication, a certain range of devices, a certain kind of performance, leads to scalable production, and the ability then to access a wide range of very high-performance technologies at low cost. To put names to some of these stages, today we're doing macromolecular self-assembly, folded biopolymers, and that's rather far along, but primarily applied for academic and biological and medical purposes, because you don't find a lot of systems engineers in the molecular sciences. It's been the key problem. Within reach, along lines of development that are now rather well understood, are positional or stereotactic assembly systems that would guide the motion of molecular building blocks, not relying purely on self-assembly and Brownian motion to align parts, but now constraining where they go. That relieves some of the design burden in self-assembly and leads to improvements in the materials that can be made. There's a cycle of advance, leads to scalable APM-level technologies downstream, and then to revolutionary applications. So the takeaway message is there. There is, we're not there. We're not within a step or two of there, but there is a visible pathway. The length of time, if one came out with a number there, it would be a prediction. And as I've said, the body of this is not about predictions. It's about what physics tells us about artifacts and what they can do if you make them. So seeing that there is a path is an appropriate task for exploratory engineering. Speaking to questions of time and cost is not. That said, one can talk about time and cost, but it has to be recognized as a separate kind of question. So, finally, atomically precise manufacturing does seem like a road to an unexpected kind of future. Something very different from what people expect, something that will require a second look at a wide range of assumptions. And what I'm encouraging people to do today is to make a little bit of space in public discourse, policy discourse, scientific discourse, for planning steps in the research labs that have range of applications, including climbing this ladder, and putting into the range of scenarios for the 21st century, initially a small note saying that there is this other set of possibilities that needs to be thought about. And I think that as people engage, they will find that there is reason to engage deeper, and that the amount of policy analysis, systems engineering, design, and so on that people feel is appropriate given expanded knowledge will increase, and that eventually one will see a very strong and increasingly urgent program in this area. But right now, the main message is that there is low-hanging fruit in the form of available information, which I think can be understood, absorbed, judged, and when judged, is compelling. My current activity is to attempt to get over that barrier. There has been some history in this area, and if this sounds controversial, it's largely because of crazy things that were said in the 1990s and became part of U.S. politics circa the year 2000, which is part of the reason that nanotechnology was defined to be almost everything but this, and atomically precise fabrication and semiconductors. So what is called nanotechnology is important and valuable, and it's almost entirely different from this, which has been a source of enormous confusion. So, more information. This is a book that is based on my MIT doctoral dissertation. It's a big, thick work of applied physics that goes from molecular potential energy functions through dynamics, through fabrication processes, systems engineering, a lot of stuff, and it actually costs money. This is available for free. It's the results. It's a set of PDFs from a technology road mapping exercise held in conjunction with several of the U.S. national labs. I was co-leader on that, and it charts in low resolution a pathway from here to these sorts of technologies. And Radical Abundance is the book that I completed here at the Oxford Martin School that is now in print. And finally, new resource, only available for a few months, though the publication date is listed there as May. It's only been on the web for 3 months at this point. This is a 105-page report that spans a range from technical discussions through discussions of institutional considerations in focusing research more effectively, through policy considerations and implications for national interest and national security policy. The abstract is in Chinese. I'm a co-author. Dennis Pamlin, who is a Swede, who is a member of the Chinese Academy of Social Sciences, interestingly, is a co-author. A number of the participants in this are with the Chinese Academy of Sciences. So I'm encouraging people to, in the West, to make sure that suitable attention is given to these topics. You can download this report from the Oxford Martin School's website, and that Google text string will bring it. There certainly are incentives for industries in a wide range of areas to not want to see profound change that would change the valuation, for example, of resources in the ground or of established technologies, long-term capital investments, and so on. My expectation is that by the time that industry leaders take prospects like this seriously enough to consider taking some action, these prospects will have been taken seriously beforehand by policy intellectuals, by people concerned with national security, people planning research programs, and that there will be a strong force to move forward from those sources. And interestingly, no one in a position to say no. If companies in the West say we don't like this, well, the most effective thing they could do would be to make sure that it happens in China instead. So there are many parties in a position to move technologies forward. There's really no one who stands in a position to block it. And with tremendous rewards in many different dimensions, I think that the motivations are sufficient to push forward. But no doubt with turbulence for the reason you're saying. And I don't really like space elevators. People have done, actually the first calculus problem that I ever worked in earnest was a space elevator calculation using graphite whisker strength. That was a 13-to-1 taper ratio with that particular material. Anyway, there are people who are very excited about space elevators, which would be you have a center of mass, roughly speaking, at geosynchronous orbit, and mass out beyond geosynchronous orbit, and a long, tapered, very strong cable going all the way down to Earth's surface. It requires an extraordinarily high strength-to-weight ratio to have that not break and be able to carry a load. What I have not seen anyone do is to explain how such a thing can survive impact with micrometeoroids. The kinetic energy produced by breaking a fiber is like the kinetic energy of a high-powered rifle bullet. The materials that are accelerated when you break a fiber are like shooting rifle bullets at the structure, And I would like to see someone explain how you don't get a cascade failure that would be catastrophic. So the current designs, I don't believe, work. Someone may be clever enough to come up with one that does. And I think there are better ways of getting things into space. So it's a qualified yes.
So here you kind of mentioned that the current physical limits associated with computations are ridiculously high. Elaborate on that?
I believe the best I've heard of, or the most best known, are from Seth Lloyd, who's at MIT and has done a lot on quantum computation. And they're taking fundamental physical constants and putting together dimensionless numbers, and they're 10 to the 30th or 10 to the 300th operations per cubic centimeter or per cubic nothing. I'm deliberately speaking very loosely to point in the direction of numbers that are by any reasonable standard of behavior of physical